Good morning. So once again, the question always is, what's the last thing in your notes from last week? We're going to pick up, that came up with a nice little assignment for us. We're going to pick up right where we left off with those notes, and then we'll move forward. So what we had was kinematics. We had a number of things, but we had kinematics, and we had taken it through the centripetal acceleration. And that was a derivation that was kind of unexpected because we were talking about the near-Earth orbit. But we did find centripetal acceleration, b squared over r. So that was familiar to all of you guys, right? B squared over r, you'd seen that before. Yeah. So then we also had numbering things as usual. We also had the curvature of a function by way of the Taylor expansion. So this picture here, I'll try to make sure it's pretty accurate. So we have a circle of radius r. We're in the xy plane. And the way we've designed this is that a function, I'm just going to do this in the blue, we have something that nests with that function. So this can just be any old function, but it's designed to perfectly nest with the circle of radius r here at the origin. And if we do that, what we find is, we've got this function y equals f of 0 plus f prime of 0 x plus 1/2 f double prime of 0 x squared. So that would be the series expansion, Taylor expansion of this particular blue function here, this blue curve. But since we located this curve at the origin, we actually have a 0 here, we have a 0 for f prime, right? We located at the minimum. And so we've got 1/2, and what we discovered was the second derivative of this function at its local minimum is equal to 1 divided by the radius of curvature, x squared. So that's the meaning of the second derivative of the local minimum. It's a local radius of curvature. So if we want to do kinematics with this thing, we're going to do the following. So now consider, and I'm going to call this a homework. Now consider r equals, and let's go ahead and call this r of t equals x of t I hat plus y of t j hat. And what we're going to do is take two derivatives, find a sub x equals d squared x dt squared, a sub y equals d squared y dt squared. Right, so those are just the definitions of the acceleration in x and y, right, straight out of the kinematic definitions. We want to find these two and evaluate at x equals 0, which is our origin there. And what you're going to find is that you've got some x acceleration depending on how fast you're moving in x. The y acceleration should be exactly this, okay? Because you're going through a curve, a local curve, and you should find v squared over r. Now to do this, let's make sure we realize what we have here. We've got x of t, I hat, but the y of t, we have to do this. That's 1/2, 1 over r, x of t, we'll place in the parentheses, squared. Right? Because we're traversing that curve down through the minimum. And so all you have to remember, hint or note, you have to remember that you're doing the chain rule here. Okay? You have to remember the chain rule, so you know, derivative, 2x, x dot, so dx, dt, and so forth. So chain rule. And that should be a pretty satisfying result, actually. So you do the chain rule, and oh, this is j hat, sorry. Right. This means we're doing component-wise. We could also, I'll write notes also, if you wanted, you could write r is equal to x of t, y of t. You're working in the ordered pair. So these are equivalent, right? The x of t, y of t, or the x of t, I hat, y of t, j hat. Yeah, so bottom line, and you may have done this in mechanics earlier, if you traverse a curve like this, the meaning of this curvature here is tied together with the acceleration in that direction. So as you traverse this curve, you're accelerating in the y hat direction, or in the vertical direction. If you had uniform, remember uniform circular motion. When you learned this originally, you learned about uniform circular motion, you may have done it like this. If you had motion in a circle, and there are various proofs to prove that as you're traversing this thing counterclockwise, that the acceleration is towards the center. Okay? So what this discussion does, it shows it's the case locally anytime you have a certain curvature. Good. So that'll be added to the list of homeworks that we had already from last week. And I'll just wrap up the kinematics discussion just to remind you guys, we've done a bunch of free fall, and we want to know free fall really well. Let me go ahead and erase this. But I think I assigned enough problems for that, so we'll tackle them as they come through. So we have this important, before we move on, motion with constant acceleration. And free fall, of course, the original case that tipped us off, but that's such an important problem. So motion with constant acceleration, turns out you can have r0 plus u0 t plus sign here plus 1/2 squared. R naught, B naught, A are constants. Free fall just has a special case of that. R is equal to R naught plus D naught T minus, or actually plus 1/2 G T squared equal G, and then you can put things in the XY axis, like the motion, and the very simple one-dimensional case we're going to return to and discuss quite a bit, because it's going to be the limiting case of many things that we do. So these very basic formulas will be the limiting cases of a lot of our problems. Good. So I'm going to move forward into discussing Newton's laws. was preparatory to talking about Newton's laws. So next topic, Newton's laws of motion. Who remembers those?
If the motion stays in motion, it must act upon by an outside force. That's one.
That's right. So that's the law of inertia. And the word force came up. That's what we're going to work with next. So I'm just going to list here inertia, and then mass times acceleration equals net force for the second law. And for the third law, interaction, two objects interact. The force that one exerts on two is equal and opposite force that two exerts on one. So we can work through these systematically. This here though is going to be the one that we do the most technical work with. And I just want to draw attention to, it has three things here. The acceleration refers to kinematics, okay? So you have to know all manner of kinematics and stuff that we had on the board just this minute, for example. So acceleration, that's just kinematics. Then we have mass. That's something new, very important. Inertia. This semester is mostly point masses. Next semester it gets more complicated with mass distributions. Okay? In both cases you have inertia, and then force is a vector. I want to spend a little bit of time discussing the vector nature of force, and then we'll launch into here with some examples. So, vector nature of force. Brought some demo objects. This is our next topic. Let's see if we can. Yeah, I brought, first of all, a couple of scales, and I should have some strings in my box as well. String scales here. And they're labeled Newton instead of. This will do. Okay. So the first thing about force that we want to talk about is just a push or a pull, and so weight exemplifies it. You feel the force in your muscles, and actually you'll notice we're always waving things around very naturally. It's hard to give you guys these two pens here and ask you which one is heavier. You can barely tell, right? We start waving them around. Why? Why do we start moving them around if we want to know which one's heavier?
To see which is harder to wave around,
Because what does that tell us?
how much inertia it has.
Exactly, it has inertia if we move it around. If it's just sitting here, you can't really tell. On the other hand, if I have something pretty brutal like this versus this, then I can tell easily. I don't have to wave it around. Okay. So that already shows you you've got the inertia to deal with. What else do we have here? So I brought these scales, and I dropped this on here, and it reads roughly 10. If that's a kilogram, of course we know it's going to be 9.8, right? So roughly 10 newtons. And I've got these two spring scales, and let's see if they do the trick too. Yeah, roughly 10 newtons, okay. And this other one, it plays along, yeah, more or less 10 newtons. So that's just the basic definition that we're familiar with. But we want to look at this vector nature. So here's the idea or the demo that we're going to look at. If I have that little 10 Newton weight that I've shown you, if I have that hooked up to two scales like this, they're both going to read what? So reading on the scale, if I split the weight between two scales, they're 10 Newton weight.
Because if it read probably incorrectly, it's 5.
Yeah, it's not incorrect at all. 5 o'clock. Let's see if we can pull that out. Yeah, physics are a lot of trick questions, right? Trying to understand things. In fact, I can't even see this. What are we getting? You guys tell me. Close enough, 5 and 5. So that's just simple addition of forces. But what if I have my scales and the weight like this? What do you think the reading will be on each scale? Five and 5? Nice thing is we can do it right here. So we resolve that. Anybody? Okay. Who's willing to? This is the crux demonstration. Okay, here we have. It's told roughly 5 and 5. Good enough. Okay, but as I pull these apart, what do we have now? 20 and 20. Okay. So apparently when you add vectors, 20 plus 20 equals 10. Just like here, 5 plus 5 equals 10. Okay. Anyway, this is a key demonstration. And actually you can see if I had our 50 Newton scales, I could pull even harder. And what's happening here, this is a demonstration of vector nature. Force. Namely, we could decompose these. I'm going to go ahead and write 20 Newtons and 20 Newtons. Exclamation points. We can actually decompose a force into components, and that's what I've just shown you here. So we'll do a larger picture of this, and we want to do this just a little more accurately. There again is my 10 Newton. And what I'm getting is 20 Newtons along the string. That's all we know, right? We're pulling on the string and showing those 20 Newtons. And I'm going to show the decomposition. Apparently, I can decompose this vector into a horizontal and a vertical component. And once you see it, you can't unsee it, right? It's this vertical component that's 5 Newtons on each side. And if this is 20, and did I draw this right? I can measure them off. Oh, reasonably close, okay. I was just doing this freehand. The point is you actually have a geometrical relation here. So these vectors, forces add like arrows. And I would just have a Pythagorean theorem here to tell me how large, say this one down here is in this case, right? So if that was 20, and I'm going to call this fx, I would have fx squared plus fy squared equals f magnitude squared. And since fx was the unknown one here, I'd have fx would be root 20 Newtons squared minus 5 Newtons squared, and so forth. So that's what it means to have forces being vectors. So the right side of this equation is all about this, and there's a whole science of statics where you have no motion whatsoever, and you're just adding up forces as structural engineers. And we'll do forces and torques But yeah, so I wanted to talk about the vector of nature of force. And that's the right side of Newton's law here. The mass we briefly talked about already, that's that inertia, the resistance to the change of a state of motion. And the third law we'll deal with when we get there. More next semester than this semester, actually. Okay. So what we want to do is now concentrate on mass times acceleration is net force, and learn some techniques of how to solve this and understand it. Good. Yeah, this is a demonstration I show all manual classes, but if you haven't seen it before, then it's good to have seen it. So now we're into the heart of what we came here to do this semester. So we're just going to do mass times acceleration equals net force. And the first thing we're going to do is introduce some new nomenclature. Namely, we have acceleration, as we saw the other day, dv dt, d squared r pt squared, right? There's a notation you'll see in mechanics quite a bit. It's common enough you have to learn it now, and that's the dot notation. Or we have x dot equals dx dt double dot equals d squared x dt squared. So the dot is just used, I think Newton introduced that as the complete time derivative. Yes, question?
I was just going to bring up this being Newton's notation.
Yes, this is Isaac Newton's notation, but it stuck around because we're doing so many derivatives and chain rules and stuff, and this is yeah, makes a lot of because of it. So anyway, I'm doing this just for one variable. The same thing. We could have r dot dr dt, as we discussed last time. This is a collection of three derivatives, right, and so forth. So that's something you'll get used to because I'll do it. I'll mix them up because sometimes I want to, do the d over dt for various reasons, but we'll also use these dots quite often. Who's seen this for the first time today? Some not. Okay. Good. So now let's go ahead and write down a few of these forces. So first of all, we could write m r second derivative equals F, and I don't have to always write the net force. Now these forces can be functions of position, explicitly functions of time, functions of velocity. So I want to give some examples. And maybe the most basic example, F is just mg, where I've got the direction built into there. That would be the weight, that would be the one that we've been using before. Okay, F equals mg. Another important one, this time would be one variable, 1/2 kx squared. Who's seen that before? Oh, I've not seen that before. That was the energy minus kx, most all there. Okay, so what would that be? Hooke's law, right? For oscillations. Another interesting one, this will be a major part of our whole semester. F of r vector divided by its magnitude. Anybody know what that refers to? That's a whole class of forces. These are called central forces. if we take the magnitude of this, actually, referring to this here, I could say, suppose we had f of r is equal to minus g product of masses over r squared, then what would we be looking at? Newton's law of gravity, yeah. And very similar at this point, just with different letters. Product of charges 4 pi epsilon naught r squared. Cool, right? Coulomb's law. Okay, so these are all functions of position. Let's get a couple, actually one more really important one. F equals QE plus QB cross B. When's the last time you guys saw that one? Last semester. And that would be electric charge, that would be the Lorentz force, right? So what's important about this one is it brings in, I could bring in that dot notation. You know, we could say that's QE, and let's leave some room here, okay? I'm gonna put some arguments there. Plus Q R dot cross B of some arguments. Life could get really complicated if your electric field were to be a function of the position and the time, which it can be, right? And if your magnetic field were also to be a function of position and time. So this force that you guys are familiar with from electricity and magnetism actually shows the most general case. The most general case of all of these is that we would have Newton's law, mass times acceleration is a net force that's a function of the position, the velocity, and even the explicit time. So that would be the most general case. And towards the middle of the semester, we're actually going to do this one with constant E and B with a very interesting result. So one of this full generality we won't actually do, but we will pick off a bunch of specific cases of these kinds of forces. So again, the mass times acceleration, differential equation, force of position, velocity, and time. Now, yeah, and these are some of the important examples. This one here, for instance, is a major goal of ours, right? The central force problem during the semester. What we're going to do now is just start working our way through some interesting examples. Unfortunately, we've already done this one, right? We'll just work our way into some interesting examples. And we'll now start with motion in one dimension. And I can kind of warn you, it'll go on for a long time because we do one-dimensional cases of this, and then we introduce the potential energy, and we get conservation of energy, and then we do small oscillations. And at some point way downstream in the semester, we're finally done with small oscillations, and then we get to doing these other things. So we'll be spending a lot of time with the one-dimensional case, but it'll all be of great use to us. So we now talked about one-dimensional motion in one dimension, and so one-dimensional case, we have x dot and t. And the first one, we're just going to declare victory for this one. So we have m x second derivative is equal to minus mg. Right. That's the free fall case if you're just throwing a ball straight up and down in the fall the vertical motion. But we'll go ahead and write its solutions down, just because we can. We have x naught plus b naught t out of gt squared. B equals b naught b naught minus g times t. And b squared b naught squared plus minus 2g x minus x0. You know what, I'm going to put this one on the homework, just for you guys to quickly, you've seen that one before, of course, right? Just to quickly, you guys know how to get this one, anybody? Basically from these two. Solve for t in one, plug it into the other, and then you get this result. So these three are really stereotypical, right? You probably had them on your formula sheets in this 4A. So yeah, we'll get those. But these are going to be limiting cases. So the second example, we'll start with right now. We're going to do an f is explicitly f of t. This one is somewhat contrived, but actually has very useful limiting cases. So what we want is m x second derivative is equal to f naught e to the minus alpha t. What could that possibly mean? And how would we solve it? What am I saying when I put a force up here like this? It's got a bunch of good limiting cases. Any idea? Sam?
This time goes on like force increases, not force, but acceleration.
Just looking at the right side. It's true, the acceleration, force will force. But what is the meaning of this force here on the right side? How would you describe it in words? That can happen. Exponential decay is the way we'd express that. So this is a force, if we start at t equals 0, it's getting smaller. It eventually goes to 0. So this is why it's always good to have a little library of forces. This one decays exponentially. But what's good about this example is if I take alpha equal to 0, I'm back to this force, right? And so that'll be, and if I make alpha very large, it'll be a force that acts for such a short time that it's essentially negligible. Okay, so what we're going to do is solve this thing, and because it's directly a function of t, we have m dv dt equals f naught e to the minus alpha t. So now we're just going to integrate this thing. dv dt equals f naught divided by m to the minus alpha t. So this is literally just a simple integration, and we get the antiderivative of this. And we can do this. We can say v minus d naught on the left side is equal to 0 to t f naught over m e to the minus alpha. Now, we're going to write t prime, or we could use a different variable, because the argument is right here. Okay? So, the other way, you could have said I just multiply both sides by dt and integrate it, right? If I multiply both sides by dt, I have this. The integral of dv would be v minus v naught. And from your fundamental theorem of calculus, you'll also know if you take the derivative of an integral of this form where the argument's at the upper boundary, the derivative is the argument of the integral evaluated at the upper boundary. So you can be confident that that's the right answer. And now let's go ahead and do the integral. And we just have that minus 1 over alpha e to the minus alpha t prime. Both boundaries, upper and lower, are important. We get minus f naught over m alpha e to the minus alpha t minus 1. Okay, so now we're going to write it this way. V of t equals v0. Just brought that over to the right side. I'm going to flip the minus sign and get rid of that one there. Plus f naught over m alpha 1 minus e to the minus alpha t. So this one's going to be good to analyze. Okay, so we've done a couple steps. This is not yet, well, yeah, this is a differential equation, but it's not yet any special technique. We literally just found the antiderivative. But let's check the result now. Once you guys have this written down, what do we get when t is equal to 0? This is how we start checking these off. T equals 0, I have 1 minus 1. 0, that's good. B is equal to b0. So that checks off logs. Interestingly, what do we get when t goes to infinity? Wow. T goes to infinity. Roberto, how about you? So what does this function do for large t? That's why we have to know our exponential function.
Well, that was
It goes to 0. Yeah. Very powerfully, so it goes to 0. So this is a 0, and we're just left with b naught plus f naught over n alpha, which is just some number greater than b naught. Unless this had a minus sign in it, then it could be a number less than b naught. Okay. Which means that this force here pushed us for a while, but then it died out and essentially left us with a constant velocity. Now, here's a really interesting one. And we're doing more of this than math methods. But what about the limit as alpha goes to 0? This is where it gets interesting. Over here, you could have said, well, if alpha goes to 0, it's just constant force. But you come over here and you say, I can't just set alpha equal to 0. Right? Because I've got it in the denominator. I'm going to do this one, and then we'll do a little more on this, and I'll make it all work. Eventually, we'll look at our list of homework and go all line up right for this week. But what do you guys think? The limit as alpha goes to 0. So I'm actually going to put some notes here. We have t equals 0, b equals b0. So we're satisfied with that. T goes to infinity. We end up with b equals b0 plus f naught over m alpha. So that seems satisfying. But what about alpha goes to 0? Limit alpha goes to 0. Double question mark.
You got an indeterminate form, you use L'Hopital's rule.
Yeah, I have an indeterminate form. I can use L'Hopital's rule and divide top and bottom by alpha. So is everybody familiar with that rule? The other way to do this is to do a series expansion of the exponential. In fact, those are equivalent operations, it turns out. unlikely, but good. We'll do L'Hopital's rule. You know what? I want to have these up here. Okay. Let's see if I can keep these up on the board. Yeah. We'll just got room always to the right border of this thing here. So. We have E over E alpha F naught 1 minus eta minus alpha T E over T alpha M alpha. So what are we going to get here in the denominator? We're just going to get M. In the numerator, we're going to get F naught. We've got a minus sign, we're going to get another minus sign. Since we're differentiating with respect to alpha, we're going to get a T out here, so we're going to get F naught T. And that allows me to, so that was just a little calculation. So what I end up with is limit alpha goes to 0, B of T is equal to B0 plus F naught over M times E. And this is essentially this result. F naught over M is the acceleration and linear in T. So in other words, the limit as alpha goes to 0 really is simply, you know, F naught over M, constant linear growth in time. Good, so this example is really important because we're doing a systematic analysis of all these possibilities. And for the homework, we can do the following. We'll leave everything up. Do everybody see how this limit is just the constant acceleration limit? That was the important point here. You couldn't see it just by plugging in alpha. You take the limit, you get that out. So, let's do the homework. And this is perfect timing. So what we're going to do is integrate. I'm just going to name this thing star. Integrate star. To obtain x minus x naught equals integral 0 to t. In other words, you integrate the right side here, and you're going to integrate this entire thing with respect to time. These are prime. This is an integration variable, the upper boundary. And again, you have to look at the one I did and take both upper and lower boundary really seriously. Okay? And when you do that, you can check these limiting cases again, which will be pretty satisfying. Integrate to obtain whatever you get over here. Then check, t equals 0, t goes to infinity, and alpha goes to 0, just as we did right here, using L'Hopital or expansion. So when you check alpha goes to 0, this one should come out as the answer. I've erased it, unfortunately. I'll tell you what should come out and you'll recognize it. You should get x equals x0 plus b0t plus 1/2 f naught over m t squared. Right? And it's a little more tedious than this one. Obviously, a little bit more to do, but you'll see the result's pretty satisfying. And that's why this is more than just a contrived force problem, because it has these good limiting cases. And this is a skill we have to get. That's the difference between knowing physics and just knowing some mathematics. We go in there and see all these different cases. Good. So we'll consult next time as to how long this homework list is becoming. I'll go back in as well. Just keep writing these down and we'll draw a line under them, and, for what's due this Friday. Because there were a bunch last week too, right?
Yeah, you assigned 4 problems for this class so far, they're due this Friday.
So there were 2 from last week and these 2 today?
Yeah.
Good. That's not bad. We can maybe add a couple on Wednesday, but we'll see. Okey doke. There you have it.